Okay, guys, let's discuss these questions on radioactivity. Let's see how you can solve it. Please don't forget that the introduction part of this topic, radioactivity, has been posted on our channel. Yes, and so do well to watch it. Don't also forget that this topic, radioactivity, was discovered by a scientist known as Henry Becquerel in the year 1896. Yeah, that was when the topic radioactivity was discovered. Also, this scientist Henry Becquerel has two students who work under him, known as Mare and Pere Curie. In the year 1898, these two scientists, their couple, so to speak, they also discovered that radium also releases radiation spontaneously like uranium. That happened in the year 1898. So please take note of these 2 years in case you are asked. Yes. Okay, let's see how to solve these questions on the board. A radioactive material has a half-life of 10 hours. You call this your half-life. What fraction of the original radioactive nuclear will remain after 30 hours? To solve it, tell them that since we have this formula, Ct equal to Co bracket exponential minus Kt, where the K is called decay constant, or you use this formula Ct equals to Co bracket 1 over 2 raised to power of T over half-life. It depends on which you are asked. Now, because they ask you fraction that remain, you will not use this formula, because this formula say amount that remain. But fraction that remain means 1 over 2 raised to power of T half-life. Okay? Now, our T is given as 30 and our half-life is given as 10. You just say 1 over 2 raised to power of 30 over what? 10 equals to 1 over 2 raised to power of 3. When this cancel this, equals to 1 over 8. So fraction that remain is known to be 1 over 8. Understood? Yes. So the answer to question number 1 is 1 over 8. If they ask you fraction that decay, remember fraction remain equal to 1 over 8. And this is the formula. Fraction that will decay will be equal to total fraction 1 minus fraction remain. That means 1 minus 1 over 8 equals to 7 over 8. You get? So if they ask a fraction that remain, just say 1 over 2 raised to power T over this. If you are not giving half-life, note that K is equal to 0.693 all over half-life. Therefore, if they give you K and they didn't give you half-life, you just say half-life equal to 0.693 all over K. You get your half-life. When you get your half-life, you come and use it here. Yes. But this one, they gave us our T and our half-life. That is how we got it. To solve question number 2, the half-life for uranium-238 is 4.5 times 10 raised to power 9 years. How many disintegration per second occur in 1 gram of uranium-238? Please, it's important to know. Look at the half-life. That means uranium-238, for him to disintegrate to its half, it has to stay for 4.5 times 10 raised to power 9 years before it will disintegrate to its half. Wow. It undergoes natural radioactivity. So if you want it to disintegrate sharp, it means you have to bombard it with what? High energetic particles such as neutron. It will just disintegrate sharp without getting to its half-life. That is what we call artificial radioactivity or transportation. We'll talk about those in all these things in the beginning part of the video or in the introduction part of this topic. Now, let's see how to solve this question now. Number of how many disintegration per second, how many number of disintegration per second, whichever one. Look at the symbol. You say it's equal to the mass times decay constant K times Avogadro's constant. Okay? All over molar mass of that radioactive element. Now, let's get it. What is the K constant? The K constant K is equal to, we said, is 0.693 all over half-life. Half-life was given to be 4.5 times 10 raised to the power of 9 years. So 0.693 all over half-life. Now, because they say number of disintegration per second, not per year. If it is per year, you just use it like this. But they say per second. You mean you have to convert these years to seconds. How? You now say 0.693 all over 4.5 times 10 raised to the power of 9. That is per year. This means times 1 year. That is for 1 year. Yes. So times 1 year. They are the same thing. How many days make 1 year? I will change this year to 365.25 days. I've replaced this 1 year to 365.25 days. Then how many hours make 1 day? 24 hours times 24 hours. Then how many seconds make 1 hour? Times 60 times 3,600 seconds. Wow. It's big digits, so to speak. Nowadays, you have to use your calculator to sort it out. Now, if you press down step first, or you just use a good calculator, say 0.693 divided by bracket this. If you press it, what you'll be having is 4.88 times 10 raised to the power of minus 18 per second. That is the value of k. So you now say minus dn over dt will be giving you, the mass is given as 1 gram. 1 times the k constant is 4.88 times 10 raised to the power minus 18 times Avogadro's constant is 6.02 times 10 raised to the power 23 all over, what is the molar mass of uranium? Is 238. Just use a good calculator. 1 times this times 10 raised to the power minus 8 times this times 10 raised to the power 23. If you press it with a good calculator, what you'll be getting is equals to 1, 2, 3, 4, 4, 6. Number of disintegration per second. You say disintegration per what? Second. Okay? So that is about this question number 2. Calculate the energy required to effect the transmutation of reaction below. This plus this to give you this. And these are the parameters given to us. All values in AMU. That is atomic mass unit. Okay. To get that energy, we must first of all say that energy required is equals to mass defect times 931 MeV. Yes. How do you get the mass defect? Mass defect is equals to total mass of the product minus total mass of the reactant. Look at your product and look at your reactant. So what we will now do is that we say we will add this word product, this and this. We say mass of the product is equal to 79.904 plus 1.0087. That is about this and this. The mass of the reactant is equal to 74.9416 plus helium is 4.0026. That is what will give you the mass defect or the excess mass. Yes, the mass defect. Okay. When you add this, you'll be having 80.9127 AMU. That is what you'll be getting when you add it. Then when you add this, you'll be getting 78.9442 AMU. Okay? So that means this is what you get when you add up this. This is what you get when you add up this. Then the mass defect. Mass defect means minus them. 80.9127 minus 78.9442. What it will give you when you minus it is 1.9685 AMU. So you have to use your calculator and confirm the subtraction. Then the energy required is equals to mass defect times this. And mass defect is 1.9685 times 931 MeV. Yes. So Once you multiply these two, you will be getting 1.83 times 10 raised to the power of 3 MeV. So that is the energy in terms of MeV that is required for you to effect the transportation of this reaction. So that is for question number 3. To solve question number 4, calculate the original mass of a radioactive element. Calculate the original mass of a radioactive substance that is 7 years old if its present mass is 4.5 grams and half-life is 1,600 years. Okay? Original mass is what you are asked. You say the final concentration or the final mass is equal to the original mass 0.5 or half raised to the power of T over what? Half-life. Or final mass equals to original mass exponential minus KT. Now, what tells me what to use is the parameter they give me. This is my T, the time for 7 years, and this is the half-life. And this is the present one, that is the amount remaining or the mass remaining. So I will now say this is the formula I will use because I have T and half-life. I will say 4.5 is equal to CO bracket 0.5. My T is 7 years all over. The half-life is 1,600. 7 over 1,600, use your calculator and get it. 0.5 raised to the power 7 over 1,600, you get it. Therefore, you now say your CO is equal to 4.5 all over 0.5 raised to the power of 7 over 1,600. So after you have pressed this in your calculator, use it to divide this. You'll be getting 4.514 grams. 4.514 grams. That is your initial concentration. That means this is the initial concentration of that substance. Whose half-life is this? That means in the next 7 years of this substance which is having this concentration, the implication is that it must have decayed. Some part of it must have decayed to remain what? 4.5. Yes. In the next 7 years, it will decay. That is 0.014 of it will decay to remain what? 4.5 grams. So that is how to solve question number 4. We go to question number 5. In question number 5, once you see this type of radioactive equation, what you do is to get my S, add this times this plus this 31. 31 minus 27, it will give you what is here. So here is 4. This plus this 15. 15 minus this, it will give you 2. That means what you get here must be equal to what you get here. What you get here must be equal. So X is equal to what? Helium what? Atom. Helium atom or helium nuclei. Okay? Thanks for watching today's video.